Okay, so this brings us now to the topic of differentials. Okay, so we just learned that f of a plus delta x is approximately equal to f prime of a times delta x plus f of a. Okay, and this was our linear approximation. We call this the linear approximation at x. Or it's the linear approximation of a plus delta x. That's how you approximate that. Yeah, I'm actually not too much against that. I don't want to crush you, so assume good intentions on my part, actually. Does that sort of make sense? Yeah. I don't want to crush anyone. I just want, people to learn. I know that, the summer's been hard, so yeah, don't worry about that too much. But yeah, it will not be that bad. I'll talk about that in a little bit too. So, these little things, the delta x, let's talk about that for a moment. So I'm going to put in a graph. Okay, then here's my function, my f of x. And here's some point right here. Let's call that x. So here's a y value, f of x. Now, here's another point, which we shall call x plus delta x. And then here's my y value, f of x plus delta x. So it should make sense to you that if you look at those 2 points, you could draw a secant. Oops. Why is it not letting me put the nice line? If you draw a secant line between them, you get this. Okay? And if you remember, you can think of the slope as the ratio of these two sides right here. And the distance from x to x plus delta x, that's delta x. So that one side right there, that has length of delta x. Which means this side right here, what length do we want to call this? If this one is delta x, what do we want to call that vertical length? So the delta x is the change in x values. What do you want to call that vertical length right there? Yeah, delta y, exactly. Right? And do you remember how slope equals delta y over delta x, change in y over change in x? And I hope you can notice this. Here are your two x values. Notice that x plus delta x minus x is equal to delta x. If you subtract the two x values, you get the change in x. Which means, if you subtract the two y values, f of x plus delta x minus f of x, you get delta y, the change in y value. And we have learned that the derivative gives you slope, right? The derivative at x is basically a change in y over a change in x. And in fact, we write it as dy dx. Remember how the derivative is written as dy over dx? That's because the derivative gives you a slope, and we think of the slope as a change in y over change in x. So these individual dy's and dx's are called differentials. Oops, I screwed up. So these dy over dx, we call them differentials. And it's interesting sometimes to think of the derivative as a ratio of differentials, right? Like, you take that change in y and you divide it by the change in x, boom, you get the slope of your tangent line. That's not actually what happens, but we want to think of it that way. And we want to think about it this way because if we multiply this equation by dx on both sides, you get f prime x dx equals dy. And we call this the differential equation. And if you look at it, it sort of looks like what's going on right here. you notice they look very similar. One of them is f prime x dx with the differential. The other one is f prime a delta x. You have the delta. Okay, so what we're going to find out is that you can use, how should I say this? You can even like speed up the process of making certain calculations by using derivatives to estimate things, actually, as opposed to calculating actual values. So how should I explain this? Let me stop that right there.